Okay, so hello everyone, and now it's my turn to explain you and to talk about the presentation that we have prepared from the construct team, and it's all about how to make use of OpenAI machine learning algorithms with ROS robots. So that's the presentation that we have prepared here. And basically, I don't know if you know what is OpenAI, but probably it's very likely that yes. OpenAI is a company that they have released a set of reinforcement learning algorithms. And those reinforcement learning algorithms allow to train agents inside a reinforcement learning system paradigm. And what is interesting here is how can we apply those reinforcement learning algorithms into ROS-based robots? Because then we'll have two very important things that are already made by somebody else that are experts and that we can combine and get, so generate really interesting and really intelligent robots, I mean. So in one side is the reinforcement learning algorithms and the other one is the ROS-based robots. Okay, so we can, any of you, I hope that you have opened the notebook, so you know how to do it, so I'm not going to explain that. And the thing is that integrating those things, OpenAI with ROS robots, you can do it by hand, and it's okay, it's going to work. We have done so many videos before about that. But I mean, those two are very complicated things. And also we want to facilitate the people to concentrate on what is really interesting for them. For some people, it may be the development of the algorithm. From some people, it may be the development of the reward of the task that the robot has to solve. And for some other people, it will be to access the robot that they have to train, they want to train. So in order to facilitate all that integration between OpenAI and ROS-based robots, we have created this OpenAI ROS package. And you can you can clone it here, but actually you already have it here on this project. So if you go to Tools and then press IDE, and we get here the whole structure inside the Catkin workspace and the source. I have cloned here for you the OpenAI package that we have created. Okay, so if here you have a set of stuff there that you will have to have a look for closer understanding. Okay, so what we are trying to do with this package? Well, to separate the different parts of the integration between OpenAI and ROS-based robots. And so we want it to allow you to concentrate on what is interesting for you. So if you are only interested on creating learning algorithms, then you will have to only to modify the training script in the structure proposed by OpenAI ROS package. Instead, if you just want to use existing learning algorithms, so you don't have to care about this part, the training script, but instead you will have to decide to which environments, to which task you want the robot to apply the learning algorithm that you want to apply. So let's say that you want to take a QLearn algorithm that already exists, that somebody else has done, in order to make a humanoid robot learn how to walk. Okay, so then you will use this part here, and then you will implement your task for making the robot train in an environment that allows the robot to learn. Okay, so that's basically what we are doing in this OpenAI ROS package, is to separate the different parts that intervene in the integration between OpenAI reinforcement learning algorithms and ROS robots. Okay, so we have divided this the structure into big parts: the training script, and that is the script that defines the learning algorithm. So it's only related to the learning algorithm and how to apply that learning algorithm to a robot in a task that already exists. And then we have the training environments. That's the second part. And the training environments, so are the ones that provide the whole environment for the learning algorithm. And these environments are divided into 3 parts. First one is the task environment. So this environment specifies what the robot has to learn. So it's like, so we want the robot to learn how to work, for example. Then we have the robot environment. That's the environment that specifies which robot we are going to use in this task. So it means we are going to use, for example, Enrico Mingo robot in the presentation, for example. So then we'll have to create this robot environment for that specific robot. And then we have finally the Gazebo environment. The Gazebo environment is the connection of the robot to the simulation. So this Gazebo environment, it's already provided in the OpenAI package, so you don't have to modify that. You only have to inherit your robot environment from that class, and everything will be handled for you in the Gazebo environment. So you say to the robot to, let's say, give me the sensors, stop the simulation, reset the positions, reset the controller. So everything is already done here in this class, and you don't have to care. You just have to say in the OpenAI training, you only indicate that, and this class is going to take care for whatever the robot that you want to use. Okay, so let me recap. We have 4 things. First, the training script, that is the one that deals with the learning algorithm. Then the task we want the robot to train on. Then the robot we want to use for the task. And then the Gazebo connection of that robot. So in this notebook, you have information about everything here, but today in this presentation, we are going to concentrate only on this, on the training script. Okay, but below you have more information. Okay, so let's go with the training script. So what is the purpose? The purpose is to set up the learning algorithm that you want to use for making the agent, in that case, the robot, to learn. And also, you are going to select the task environment that you want to use, of course, because you need, in order to train, you need to have the learning algorithm and the thing on which you want to train. And then the task environment inherits from the robot environment. So if you specify the task environment, already got the robot defined. And what is important of the training script is that once you have defined the task environment, you can modify, you can change the algorithm, the learning algorithm, without changing anything else. So you can just plug a different algorithm there, and then the whole thing will work. And that's super useful because you can try to create other algorithms and you don't care about the connection to the robot, the task, the reward, etc., etc. Okay, so in this case, so let me see, because here I cannot see. There should be something else here. Okay, yeah, let me see. Wait, okay, it's okay. Okay, so we are going to use a Carpool. Okay, so the Carpool you already know. So let's do one thing. Let's go first to the simulation. So if you go here to simulations, and then we are going to select here, select the launch file. And here you should select the main launch in this menu here. So select launch, and what we are going to get by doing this is the simulation of the robot that we are going to use for this example. That simulation that is starting here, you have it here in the simulations workspace. So here in the IDE, you have several workspaces. And here in the simulation workspace, I have included the Carpool simulation. And that's the one that is starting here. Okay, so just in case that you want to modify, you want to check it later. And the code that we are going to create is, of course, included into the Catkin workspace here. Okay, so it's about to be shown. So let me put it here on the side also. So, okay, so yeah, so it has been a problem here. So with the controller manager interface. So strange. Okay, let me repeat the process. So it's this one, yeah, the main one. So it should start like this. Let me know if you have any problem on your simulations or something. Here is loading the controllers, spawning, and it looks like it's correct. Okay, here it goes. Yeah, so I don't know what happened previously. So anyway, we have here the simulation, the Carpool. The Carpool is a base that can move around. I see that Tony has no problem, great. And here it is again. So the Carpool is this base that can move around only on those two directions. And then it has a pole here that has no control. So the task of this base is to maintain the pole straight by doing small movements in one direction or another. It's like when we were doing this as we were kid in our hand. Okay, so let's make a system that learns how to do that. For that, we have the simulation, and now we are going to create the training script for this. Okay, so all the task, in this case, the task environment is what I just explained, is hey, please learn how to maintain the pole straight. And that is specified in a task environment that is already created for you. Then we have the robot environment that is this specific robot simulation that is also created here for you. And then finally, we have the Gazebo environment that, as I said, is for any simulation, is the same. And it's already provided. It's the connection between the simulation and the Gazebo environment, etc. Okay, so now let's go to create the training script. Here we have the code that we need to use, and we are going to create it, and then I'm going to explain that to you. So for that, go to the IDE, and here in the Catkin workspace, if you go to source, then I'm going to close this OpenAI ROS package. You can come here to my Carpool training. I have already created this for you in order to speed up a little bit things. So you have this package that is the one that is going to contain our training algorithm. Then it only contains the basics, okay? Just contains the training algorithms that we are going to use. So these are the specific reinforcement learning algorithms, okay? These are not the training scripts that we mentioned here. What we are going to create now is the training script that uses those reinforcement learning algorithms. Okay, so let's go to the source and then create here a new file, and let's call it like it is indicated here in the notebook. So it's start underscore training.py. And then if you open it, in double click, I'm going to put it like this and this a little bit bigger. So you can select the code here in the notebook of this cell and paste there. So just select the cell and then do Control-A to select everything, Control-C to copy, and then come here and then do Control-V. So you have the whole code there with a proper indentation. Okay, so you can also do it like this, so selecting, but that method I explained is faster. Okay, so we have the code here. Great. Let's see step by step what is doing this code. Let me put it bigger. Okay, well, first of all, it's importing from OpenAI ROS, our package. It's important the Carpool stay up environment. So this is provided here in the OpenAI ROS. So our package, OpenAI ROS, already provides for the Carpool, the environment, and the robot, the task environment, and the robot environment. So you can have it here. Actually, we have at present for two robots and tasks. One is here, the Carpool to stay up, and another one is for the moving cube. that it's a, if you follow us in our YouTube channel, you can see that this is some project that we are doing now, and we are posting in our YouTube channel about a cube that has to learn how to move, etc. Well, anyway, so here it is the task environment that describes what we want the robot to achieve, how to provide the reward, how to get the observations, how to apply the actions, all that. It's explained there. So we are importing this from our package. Then we initialize the node, of course. And then what we are doing is to create the OpenAI environment. So that thing that we have imported here, we are creating an instance of that here. How do we do that? By specifying this sentence here. And this name here is exactly the name that is defined on the environment. So if we open here the stay up environment, this stay up that is for the Carpool. So if we open that file here, you will see that at the beginning of the file, you can get this register. And with this register, we indicate the name. That is the name of this environment, and that is the name that is going to be registered into the OpenAI system. And by being registered, you can use it on any training script that you want to create. Okay, so here you have this environment that we are creating for the Carpool. Okay, so what else? Here we are just setting the login system for a specific directory. So it's going to create a training results directory and put all the results of the training, the different rewards and the different steps and episodes, etc., etc. That is not very important for now, but just have a look at that if you are interested. Then here we have something that is interesting. It's all this get param, get param, get param. So what is that? Well, as you probably know, in reinforcement learning, you need to specify the parameters that you are going to use on the reinforcement learning algorithm. So in this case, we are going to use qlearn for learning that task here. For learning the task here, we are going to use qlearn. And that qlearn has some parameters, the alpha, the epsilon, gamma, the discount, and those you have to specify. So how do we specify? I'm going to show you in a minute. But what we are doing here is to retrieve those parameters. This is the get param. And we obtain those parameters from the ROS param server. Okay, how do we get those parameters on the ROS param server? Well, we go here. Let me show you on the notebook. Here. It's because we are creating a Carpool qlearn params YAM file. And inside that YAM file, we are putting all those parameters. As you can see, here are the parameters for the reinforcement learning algorithm. And those are the ones that we are retrieving here. As you can see, the alpha, the epsilon, the gamma, number of episodes, etc. And so those are specified in that config file. This is very important, okay? Because reinforcement learning algorithms are very good, but only if they have the proper parameters. And finding the proper parameters is a task in itself. So it's a problem in itself. So you can have the very powerful algorithm, but then if you don't have the proper parameters, it will not work. So we are going to learn more about that, how to find those parameters later in some minutes. But anyway, here in the training script, we are getting those parameters, okay? Then once we have those parameters, now is when we are creating an instance of the learning algorithm. In this case, we are using a qlearn algorithm, but it could be any other reinforcement learning algorithm. We are using this qlearn, and this qlearn, we are getting this class from an import. Here, where it is, let me see, here it is, qlearn, import qlearn. And this QLearn implementation is provided by us here on the Carpool training environment. So it's here the file that does the QLearn implementation that you can see here is made by Víctor Mayoral Vilches from Early Robotics. And we have included here for easiness. So that's the implementation of QLearn, a learning algorithm, okay? So we have that here. Here is where we say, hey, we are going to use this for learning. And now we start, apart from several details here, several variables that you need, we are starting the training. Then, as you know, the training, it starts from by doing several episodes. An episode in reinforcement learning means a trial. So in every episode, we say to the robot, hey, robot, please try to maintain the pole straight. And then we give some time to the robot to try that, let's say 30 seconds, or a certain number of movements. So basically we say on this episode, you have 30 seconds, then try, or until the pole goes down and touches the ground. So then try, then it tries, and after he has tried, then we compute the reward, and then for that trial, and then we repeat again with another episode and say, okay, so you did it this good or this bad, then try it again. And then we repeat again the same process for the 30 seconds or the number of steps. So this is the first for loop that we have in the training. That is the one that specifies the number of episodes. So where do we specify that number of episodes? Is here also in the configurations parameter. So it's the number of episodes that we have here. So we are allowing 1,000. Then for each episode, each trial that is trying, then we say, hey, how many steps, how much time I have to try this? Then we say, so you can try this number of actions, this number of steps. On every step, the robot is going to take one action. Okay, so this is the number of steps of actions that you can take, robot, for a single episode. Please try. Okay, so in this case, if we go here to the tutorial, we have that the number of steps is 1,000 also. Okay, then once it starts to try to figure out how to do it, the robot, then what it does, it's first, it goes to the QLearn algorithm and says, hey, please, from what you have learned, give me one action. What would you do? Learning algorithm, what would you do in the current situation? And then it provides the state. The state is the current situation of the robot. And then it means what the sensors are saying, what are the previous actions. It depends on how you have defined the state. The state is defined in the environment, in the task environment class. So it's there where you define that. So in this case, the state was, let me check here. So I think we have it here below. And the state, don't remember, get the observation. Yeah, so the state is here. Okay, let me see, get the observation here. So the state is the base position, the black thing, that's the base, and that's the pole. So we have the base position, the base velocity, the pole angle, and the pole velocity. Okay, so that's the state in this case. So again, we go back here to the algorithm. Here it says, hey, choose an action based on the current state. And then it provides the action and says, okay, execute action 3, for example. And then the next thing that it does is to call to the environment and say, hey, please, environment, task environment that contains the robot environment and the connection to Gazebo, please execute the next step by executing action number 4. That is the one that we have selected here. And then the environment is going to select this action, execute this action in the robot, in the simulation, as it is specified in the task environment and the robot environment. It depends on how it has been specified there. So it's going to execute that and then compute the reward and the next state. So it's going to say, based on this action I have executed, then I think that you have done it that good or that bad. And the next state in which the robot is, so the current velocity and position, etc., is this. Okay, so basically then we add the reward and we compute all the reward, but basically that it is. So basically that's it. So this is, well, the only thing that remains is to use that for learning. So in that case, so after we have selected this, taken the action and obtained the reward and the observation, we say to the algorithm, hey, please learn new information from the current state, the last action, the reward, and the next state, so the state after the action has been applied. Okay, learn, and this is where the QLearn algorithm is learning, making the robot learn, and then it repeats the whole thing. You can see here more things about if the task has been done, because then stop the learning. And done, it means two things. It means that, well, it basically means that the robot has failed, or that we have reached the 1,000 steps. So if the robot has the pull down, then we are done. Okay, so we have, that's the training script that we have. I don't know why it shows that I have done some modification here. Oh yeah, so because I didn't save, yeah. Okay, so remember to save, okay? When there is this dot there, it's indicating that you haven't saved. Then you can do Control S or come here and save. Okay, so we have this start training algorithm done. Then let's go continue on the notebook. Let me go. When we created this, so we have this training algorithm, training script, sorry, that uses the training algorithm. In this case, is the QLearn. Okay, so now we have that training script. And as I mentioned, we have to create this config file. So let's go and create that file. For that, we go here and on the Carpool training, create a new directory, new folder, call it config. And then inside there, create, right click, create new file. And the new file name is specified here. So please use the same names as we are indicating here, because otherwise the example cannot work later, because we are assuming something. So let me change the name here, Carpool QLearn param. Okay. Then I'm going to open it. And I'm going to copy the content of this config. See, Control-Alt, Control-C, and come here and paste it. So here you can see that there are two types of parameters. Ones that are the ones that are related to the environment, and other ones that are related to the algorithm. So you don't have to specify parameters always. It doesn't matter. It depends on your situation. In this case, by applying these parameters, you can modify a little bit the environment. The environment means which control you are going to use on this robot, what is the minimum pull angle, the maximum velocity allowed, the time of the running step, etc., etc. You have to look at the documentation of the environment in order to know what those parameters mean. And it depends on every task that you want a robot to execute. And the same happens for here. It depends, those parameters, they do depend on the reinforcement learning algorithm that you are using. Okay, so we have this and the configuration, and let's go, and we have to create a launch file that is going to launch the whole thing. So for that, let's create one launch file that is called start training launch. So you go to the IDE again, and here inside the launch directory, create a new file called like start training.launch. Open it, and then go and copy this code here. What is this code doing? This code is doing just two things. First one is loading the learning parameters into the ROS param server. And second is launching our script, our training script. That's it. That's it. And I think that there is something wrong here. Okay, so here, I don't know if you have this error here, but there is an error here with some lines. You have to remove those hyphens and the greater than sign. So I don't know why they got there. Anyway, yeah, I think that the rest is okay. Okay, so let's save it, and then what it remains is to launch it. So let me hide this. Let me hide this. And let's open a shell here. Select on the tools, shell, and then let's do the ROS launch. Let me see, ROS launch. The name of the package is called my package. My Carpool training, and then start training launch. So you can launch it, and then the ROS should start training. And now it has crashed because it says no module name OpenAI Carpool. Yeah, that means that we haven't got the OpenAI ROS package. We haven't sourced its content in the ROS system. So we have to go to the Catkin workspace here, and then do a Catkin make in order to compile what is included and is provided into the OpenAI ROS package. So it has to compile everything, and then let's see. It's taking a while, but it's yeah, okay, done. Then once you have that, you have to source the content of this Catkin workspace. How do you do that? Then you type the command source, then devel/setup.bash. Okay, now we have all the content, and then we can relaunch the training script. So I'm going to do it right now. And then as you do, okay, so resource not found. It says ROS package, Carpool 0 training. Okay, so we have something wrong here. Let me see. Maybe it's because of the test that we have been doing. Okay, yeah, sorry. Yeah, that's a final change that we did. So in this case, you don't have to get the Carpool V0 training. This is not the path. So the path is the My Carpool training name, because we changed the name of this package on the last minute. Okay, so come here to the line 29, sorry, and change here, instead of My Carpool, just put the name of your package that is called My Carpool training. Yes, save it. Be sure to save it, and then let's launch it again. Hope that this is the only problem. Okay, so let's go. And here, the robot is starting to learn. Okay, starting to train. As you can see, the robot is kind of moving the base and trying to maintain the pole. But of course, it's failing. And when the pole falls down a certain amount of degrees that was specified in the config file, then it considers, hey, you fail. Let's start again. And then the system restarts the simulation, puts the robot on the same position, etc., etc. And it does everything. And one interesting thing is that while this is being produced, there is a topic that is called OpenAI/Reward that we are publishing. That is including to the Gazebo environment class. So if I go here, let me show you. So inside this package, OpenAI ROS, this class, Open Gazebo environment, is taking charge of publishing into a topic that is called OpenAI/Reward. So it's publishing the reward all the time. And here, specifically in the ROS Development Studio, we can go to Tools and open this OpenAI Reward chart here. So if you open, you will see how the reward is being plotted for all the training iterations. So it's getting now, it's reading. Yeah, so it's one after each episode. So if I change here to the Gazebo, so yeah, so you got this, and it's starting to plot how you can check. By doing this, you can check if the robot is actually learning or not. So that's something that you have to check, because maybe you have a system that is not allowing the robot to learn. Maybe the environment is not proper, maybe the reward is not proper, maybe the parameters are not proper for making the robot learn. Okay, so if you leave this for a certain amount of time, then the robot will learn. But I think that we have to leave it for, I don't remember exactly the amount of time, but like 500 or 1,000, between 500 and 1,000 steps in order to make it learn. Like this, take into account that this is a lot more complicated setup than the typical Carpool example of reinforcement learning, because here we have all the controllers in the middle, we have the ROS messages passing, so it's a more closer example to reality. So it takes longer to the algorithm to learn. Okay, so one thing. So let me go here while the robot is learning there, and you have seen the reward. We'd like to talk something about the reinforcement learning parameters. So here, you guys seen that we have many parameters there. And as I mentioned, let me see the training parameters. No, here. So, and as I mentioned, finding the proper ones can be a nightmare to find exactly which ones are the ones that provide the faster learning or even allowing learning at all. So in order to do that in a faster way, we have integrated here a tool that we call the gene computers. And this is some feature that maybe you attendants, you cannot actually execute because this is still in beta state. So we are not allowing this for still to the general public, but it's going to be released along the month of July. I just wanted to explain you a little bit how it works. Then on the gene computers, what you can do is to launch the same simulation, the same training with different configuration parameters in a parallel setup. So you launch a bunch of computers, each one with different configuration parameters. So you can check in real time which one is better than the other. So you don't spend so much time here waiting for 500 generations in order to change the parameters. So how does it work? Well, you go here to the gene computers and then you say initialize gene computers. Then, so it's going to start here, system. So it's loading some the simulation workspace launch files, and it's taking some time. So remember that this is still in early beta state. And let me see, because it's kind of stuck there. And I'm going to stop this chat there because I'm getting many messages there. Okay, so I don't know what is happening here. Maybe something got stuck. Let me refresh this. Okay, restore. We have here the simulation, and I have stopped the script, okay, by doing the refresh. No problem. No problem. Okay, so let me try again. So we go to Gene computers, and then we initialize the Gene computers. Oh, here it is. Okay, so don't know what happened. Then in these Gene instances, you have to specify which simulation are you going to use for the Gene computer. So I'm going to select here, for example, my simulation, the one that I'm using it. So it's the one main.launch, the same I have launched it there. And which one is the learning algorithm? Actually, the learning script. The launch file that is going to launch the training script. In this case, is the start training launch that we have created there before. Then it will ask me for the number of computers that I want to launch in parallel. In this case, I'm going just to set to 2 to simplify the process. Why? Because now once the system knows which one is the simulation, which one is the training algorithm that we want to launch, and the number of computers, then we hold here, and then it's going to look for YAM files. Okay, so YAM configuration file. So I have to close here because I only have one YAM file. That is the one that we have created here with those parameters that you can see on the screen. That's the ones that you have used. But imagine that we want to modify this and check for other parameters. So what you would do is to create another file. So let me duplicate this one, and let's call it one. Let's call it 1, and the other one, let's call it .2. So in the number 2, I'm going to modify, for example, in the algorithm, instead of an alpha of 0.5, I'm going to put an alpha of 0.7 because I want to see if it's learning faster with this alpha, for example. That's the only change that I want to do. But I could change many, many things if I want. Then I save this one, and then I go back again to Gene computers and say, initialize the Gene computers. I want to launch the simulation of this main launch. I want to execute the learning algorithm that I have created with this launch, and I want to use 2 computers. Then I do next. And here I select, for the computer 1, I want the configuration of the parameters number 1. For the computer 2, I want the configuration of the parameter number 2. And then that's it. So now the system is going to launch those computers and launch the simulation with the training algorithm and the proper config there in parallel to the computer that we have here. So everything that is done, and then so they are being initialized, and then it's going to take some minutes to get ready. So in order to show you how it looks, I have put it here some videos because it's going to take some time. So let me see. So that's the process that I have described it here in the notebook, so you can follow then. But here I have a video. I have included a video that describes the whole process, how it works. So let me just play it and show that to you. So you connect to the, when they are ready, you are launching, and then at some point in time, let me move it forward. Okay. Let me move it a little bit more forward. So yeah, so here, let me show you how it was. Okay, here, wait, here it is. So at some point in time, I'm going to have here the computers that still are getting set up. You guys, you can see here. So the 2 computers that have launched. Well, so in this case, I am selecting one computer on the other, and wait, sorry, web. Then when I select one computer, I'm going to get the window of that computer open, and I'm going to see how it is training the robot in that computer. And then when I select the other computer, I will see what is training on the other computer. So I can see in real time how the training is being working on all the parallel computers and everything under the same environment. And you can see the logs also, select the logs and the different options that you have there. So basically, that's what happened with the gene computers. And once the gene computers have finished, they will store the results into the AIWS directory. So this video shows how. So I cannot show you very well because it's very small here, but you can see better in your own screen the video. So basically what it does is when the system has finished, it will store the results inside this directory, and the results are stored containing the reward and also the config files that lead to that reward. Okay, so basically that's it. So you will see the rewards there. So afterwards you can save the whole project and you will have all the results of all the tests that you have done. Stores by date and containing the configuration parameters that lead to those results. So everything is organized in that sense. Okay, so we are about to finish, and what I would like to show you is this is an exercise for home. So the power of this method that we are providing with the OpenAI ROS package is that you can change, for example, very, very simple way, the training algorithm from Q-learning to another. We have provided here another algorithm that is called the SARSA. He's here, and what is my homework for you is that you go here to the start training algorithm script and then change the Q-learn by the SARSA and do the same thing. As you will see, you will have to change nothing, not the simulation, not the robot, the way to communicate the robot, etc., etc. So that's the power of this approach. And here we just would like to finish by explaining you the structure of the system that we have created within the OpenAI ROS package. And it is that is the following that is here. So on one side, we have the robot that is simulated. And then we have this Gazebo environment class that is the one that connects to the robot, to the simulation. It connects to the simulation and then allows to reset the robot position, to set initial positions, and to perform all the steps in the simulation that are required when you are training. Then this is independent of the robot. This is in general for any Gazebo simulation. Then we have the robot environment that inherits from the Gazebo environment. And this robot environment is the one that provides the specific things, specific actions, specific sensors, actuators for that robot, and in particular. So there has to be a robot environment for each robot that we want to control using this package. We are creating all the robot environments for other robots. At present, only have the Carpool, as you have seen, and the Q robot. Okay. Then the next one is the task environment that inherits from the robot environment. And this task environment is the one that specifies what we want the robot to learn. And of course, depends on the robot. So if you want to modify the robot, then you will have to modify this class and also the task class. Unless you change the robot and the robot provides the same interface. But basically, you will have to modify it most of the times in the task environment. The task environment, you specify what the robot has to learn. And then we have the start training script, that is the one that we have created here, that contains the learning algorithm. So you can change the learning algorithm and plug it here without changing anything of this chain. You can modify the start training if you need it for something special of algorithm without modifying the rest of the chain. And that's the same thing. You can modify the tasks without having to change the rest of this. Or you can modify the robot environment without having to change all that. That's what the type of encapsulation that we wanted to solve here. You have more details here about how to create a task environment for your robot or a robot environment, and here, so you can analyze later and see it later. Okay, so that's all from my side, and I'll be happy to have some questions for you. To answer some questions, sorry, for you. Thank you.
Very nice. So if you can unshare your screen so we can see your lovely, lovely, lovely face.
I'm trying, okay, but I don't know what is happening here.
No? What?
Right?
Where is Ricardo? 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 Hello, Ricardo. Ricardo, can you hear me? Yes, I'm here. I'm here. Yes, I'm here. I'm here. I'm here. How you doing? How you doing? I'm here, ready for the questions. Okay, so questions. Yeah. Let me know. I just travel the space and time to be beside Miguel. So, any questions? So, Timo Kurzels has many questions. Okay. So, first question: Is it possible to have multiple Gazebo instances running in parallel, which feed the same learning algorithm to speed up training? As you have explained, the gym computer runs parallel instances with different parameters. Exactly. So, I don't know if I got the question properly, but if you want to have several instances of Gazebo, feeding the same reinforcement learning algorithm. Okay, in that case, so it's possible you have parallel computers, and on each computer you have one Gazebo running. Or also you could, for example, Dockerize Gazebo in one single computer and have several instances of Gazebo in that computer. And that would be very slow, I presume, because Gazebo takes some resources, but it's theoretically is possible. And then the only thing that you will need is that your reinforcement learning algorithm can get data from those simulations and make sense of that. Because, I mean, it's difficult because the reinforcement learning algorithm is controlling one single agent. So I don't know if there is any reinforcement learning algorithm that already allows you to take information from different robots at the same time and learn from all of them at the same time. I'm not aware of that. So that's the top of my knowledge. Sorry. Okay. Any other question? Second question. Yeah. From the same user, do you have experience with moving out of Gazebo to the real world? Because it's not the best physical simulator for some sensors. This is why NVIDIA comes up with Isaac, I guess. Pitfalls or recommendations on how to do the transfer learning. Okay. Yeah. So that's a problem, real, because if you train on the simulation, what happens is that usually the training algorithm gets used to the way the simulation works. So it adapts too much to the simulation. Then there is something that is called the reality gap. And that is the difference between a simulation and the real thing. So let's say the simulation of a robot and the real robot. That difference is called the reality gap. Then your training must be strong enough in order to cross this reality gap. Or otherwise, if you don't have this training properly, then what it works on the simulation, it will not work on the real robot. Then for that, there are some techniques that have been developed and for trying to transfer this reality gap, to jump this reality gap. There is a very interesting paper on that from OpenAI that is published on their website. Please have a look because it's about how to transfer. I don't remember exactly the name, but it explains exactly that thing. So have a look at that. Okay, fantastic. And I think last question. Okay. So this question, let me just a second. Yeah. So Simon. I would like to hear Ricardo's take on some of the issues, challenges when setting up your robot model environment in Gazebo. Example, the issue of
resetting the world robot for each training episode, and perhaps other tips and tricks when Gazebo is not working as expected. Yeah, okay. And because here developers may experience some challenges when they want to make their own Gazebo environment for reinforcement learning.
Yes. So well, you hit the point, because that's difficult. Yes. But it's not only happening with Gazebo. I mean, it's happening with any simulator. So you have problems. So let's go step by step. First thing, we try to separate all that for you by using the Gazebo environment class that I have mentioned there, and that you can see on the OpenAI ROS core. So if you use that class with OpenAI algorithms, it's very focused on OpenAI, okay? So you need to be within that framework. But if you do that, then I can tell you that you can forget about the Gazebo issues, most of them. You cannot about crashing. If Gazebo crashes, no. But I'm going to explain about that also. So if you want to use Gazebo within OpenAI, use our Gazebo environment class that allows you to reset, to execute at one step, to connect to the simulator and put initial positions, etc., etc. This is all handled by that class, so you don't have to care about. And if you find a bug, please report that to us, because we are publishing this for everyone. So we want that this is strong for everyone. Okay, so that's the first thing. Then about other things like crashes or just start the simulation, something like that, that's real problem. So your learning algorithm has to be strong enough to save the state at a certain point and then restart learning from that point. So that is very important when you're working with simulations. This point is very important. So you may think, oh yeah, it's learning, let's leave it like that. No, if you got the system learning and working with a simulation, then quickly, you have to work on how to save the environment, the current learning status, let's say, and how to restart your system from a certain point, because those crashes are going to happen. They are going to happen. And it happened to me in my PhD thesis, so I had to deal with that. And I was using very, very good simulators, but that's happening all the time because we are stressing those systems, So then at the end, the thing is that so you're going to have crashes. So you don't want to have to start again from a training of 2 weeks. I was listening to one presentation of OpenAI. Well, they were training their agent for playing to Dota 2 game, Dota 2 game. And yeah, they had to leave the algorithm training for 2 weeks. So imagine if you have a problem there. So you lose 2 weeks and then you have to start again. So it's very important that you set the saving at every step. That you got new knowledge, save it.
Yeah.
You got new knowledge, save it, and then have the recovery mechanism. So what I recommend you is you don't think, hey, okay, yeah, if this crashes, I have it saved. So yeah, I will do manually and recover. No. Do it something automatically, because this is going to happen and you're going to save a lot of time and of problems.
Yeah, and if, for example, if you use an algorithm, a more complex algorithm like deep learning algorithms, they normally do periodic saves each, I don't know, like 20 episodes, so that if it happens you don't lose all the learning, so you only lose the last 20 episodes. Okay, yes, right. I'm not sure if this is automatic in the DeepQ learning, in the reinforcement. I don't know the setup. Yeah, so
it does. In the DeepQ, it does automatically. That's great. In the Q learning, it doesn't, but you have functions inside OpenAI to do the saving and then the retrieval afterwards. Look for them on the documentation of OpenAI.
Okay, so we're finished.
Yes.
Yeah.
Thank you very much.
Thank you very much.